Good morning.
Morning.
Yes. So, are you experiencing this storm that I've heard about in the U.S.?
Yeah, it's been raining pretty hard the last several hours now. It's a lot of water in our yard here.
I see.
How's it up there?
Right now, it's quite okay, but it's predicted that within about a day, we'll be seeing snow from the same storm.
Huh. Well, we're not getting any snow here. I'd like to see some snow, but doesn't look like we're too far south, I guess.
Well, at least when you get the snow, you can enjoy it, and then it melts and it's gone, right? Yeah. Here, if it snows, then we have to put up with it for several weeks, if not a month or more, before things improve.
Yeah, I guess it's time to get tired of it by that time.
Yeah, so we're pretty much, of course, in the middle of winter at the moment, so it feels like it lasts a long time.
Of course, the first few days is when it's snow white. Then it just gets muddy and all dirty.
Yeah. Yeah, or icy. Ice is a problem here often because it does get warm enough to rain, but then the next day it'll be 10 below Celsius, and it'll be all frozen and slippery and difficult. Makes things difficult. Snow is not so difficult. You can always, there are machines that you can use to move it around and so forth. Right? But ice is another story.
Do you ever go ice skating?
Oh yeah, not in recent times, but when I was younger, it was quite common.
Ice skate, but
Where I worked for quite a few years in Ottawa, the capital city, they have a canal that goes through the center of the city, and that canal freezes every winter, and it makes a 7 mile long skating rink. So in fact, I used to live almost at the far end of this canal, and I used to work on the other end. So I'd get up a bit earlier and put on skates and skate to work. Although that was, I should say that was probably 40 years ago. So.
Right, time goes by.
Yeah, it does. So how are things with your research?
Well, I've made some progress, but I'm trying to, I'm trying to finish a paper for this ICA CGA thing. It's supposed to do at the end of the month. I'm not really ready yet, so.
Was this the
I did
paper?
make some progress on. I can send you a sheet on it. Finding these symmetric products with 1/2 and minus 1/2. I can tell you what geometric algebra is associated with them now.
Oh, that's good. Well, is this related to the same paper that you presented in at that conference?
Yes, it is actually. Of course, it's related to what we've been doing as well. Okay, I see that Dr. Cruz Jesus Cruz is on now. So
yeah.
How?
Good morning.
Good morning. Good morning. How are you? Yeah.
Pretty good. How are things down there? Is it? I guess it's warm in Mexico.
Oh, not too much, because inside home we have not
Yeah, I know.
calefacción, and then we are cold inside home.
It's warmer outside than inside.
Yeah.
Mm.
Of course, you get high altitude in Mexico City, so you it could be warm if you were in the valleys, perhaps, but not so much in Mexico City itself.
Yeah, Puebla is the same. It's at over what 2,500 meters high, and as long as the sun's out, it's warm. But when the sun goes away, it's cold.
Yeah.
Yes, we have many changes of temperature in the day. Then in the morning early, we get sometimes around 0 degrees. And at the half of the days, around 25, then it is too much.
Big change, yeah.
Yes. Mhm. Mhm.
Well, how is we've been away for a while, so I think you must have had a lot of opportunity to prepare a lecture for us today, Jesus.
Good. I don't get too much for this, but I am going to show to you some okay.
So we've been talking about graph theory for a while.
Yes. Okay. I'm going to first. We are going to okay. Here, you have the title, complete graph and dots. Do you have now?
Yes, that looks fine.
Okay. Mhm. Because the idea is to connect with Clifford algebra, but I not get too much in this way. Then first, okay, again the definition of graph here. Like a relation between two kinds of sets, E and B, edges and vertex. Then this relation is established with one function that are P and P defined two different kind of relation that are target and source. Okay, this is the first idea. With this idea, we define and this is important. Here, another way of seeing this is like a collection of cells. That is, B is a cell and E are cells too, but of different degree. Then we have 0 cells and 1 cells. And then the relation is between cells. All of the sign category of cells, but of different degree. Then a graph with n vertex GO is a 0 cell graph. This is this 0 cell graph that we have here. Is only a set of vertex, but a set of 0 cell graph. And here we establish one cell graph that are all the possible relations between between the vertex. And then we define here the graph, one graph, establishing the required relations between the vertex. Then we have, we can say, different kind of possibility of relation between vertex, but those, not all of those are defined in the one cell. In one cell. Then we have here one example of one graph that are the definition of source and targets between the different kinds of vertex. Okay, with this definition, we can generalize this relation, the relation here, but now with different kinds of cells. Then here we can see how to get a general relation between different degree of cells. Then the idea of graphics here is too much general, because each vertex can be some complex graph here, and then we have a generalization of the idea of graph. Then we define either two kinds of functions, source and targets. Between these two generalized cells in the graph. Okay, this can give to us a more general idea of graph, and then we can speak about one n graph, not yet here, excuse me, about one n graph. Not emphasized enough here. I need to put this here, but this is exactly an M graph, where M is a integer. Then with this, we can generalize to the idea of n graph, and then this idea of n graph is for relate in the same way that we see before, to more complex relation between different kind of n graph. Then the idea is the generalization to graph of graph, or multigraph of multigraph, in this kind of relation that we have. I wanted to show this before, because for speaking about a complete graph, I think that it is necessary that we use this kind of concept. When we speak about one complex complete graph, okay. Here, when we have a complete graph, we have here a complex of relations that is necessary to describe in the way that we made of in terms of n graph, for the purpose that we get one one first a category and then an algebra structure on these relations. Then I have not here excuse me. I have not here the more material, but the idea is expressed in this graphics. I started here with that more simple graphic. I cannot. I don't know if I can mark on this. No, no. I cannot make annotations with this computer. I need to use my another keep for that. But the idea is that starting with this graph, we can have here different kind of cycles here. Then this cycle are defining for us one kind of relation, and we can get different travels for getting again the one dot. Then we can go from 1 to 2 and from 2 to 1, but we can go again from 1 to 2 and from 2 to 3 and from 3 to 1. And those are complete cycles here that are represented different kind of transformations. Maybe I can put this in my other equipment because I can make a notation here, and I like to make some of this.
I'm not sure what computer you're using, but on my computer, I have something where it says view options, and I can click annotate, and then I can add annotations to your graph.
Yes, maybe it's my software here because no, it's only annotations, but I can make some freehand drawing. Okay, excuse me.
The type of graph that Dr. Sobchak has been talking about is a directed graph, but not complete in the sense that you have defined completeness. Right? He has a single edge between each node, and that edge has a direction. Right? So it's what he called a complete graph is a subset of what what you've defined.
Yeah, I wanted to name vertices of a graph with null vectors. And then if you take the inner product of any two vertices, then it's either plus 1/2 or minus 1/2. But it doesn't look like you can, with such a system, you can have two edges, one, like he has a complete graph. Each vertices is connected by two edges, one going in one direction, the other going in the other direction. And I'm not sure
Oh.
whether that would be possible with.
Well, perhaps it's what you would like call a null, like, so where the scalar product is zero.
Yeah, maybe that would. Yeah, I suppose you could do that. Maybe. Yeah, if you like. I just have a couple of pages. I can show the relationship between Clifford algebra and these null vector vertices, if you want me to. I did. I have a couple of pages that I could show. If you want to see the relationship between Clifford algebras of the form 1, n, and also n, 1. So with 1, n, that's where you have one vector with positive square and n vectors with negative square. Then that corresponds to this, where all the inner products of these null vectors are equal to 1/2. And if you have the inner product of the vertices equal to minus 1/2, then that corresponds to the geometric algebra n, 1. Which is, it seems, it works out very well that way. But for the most general geometric algebra, there doesn't seem to be any direct. Well, maybe it could be worked out. Just as you say, you can have vectors which are all, so all your points, vertices are null vectors, but you can have the inner product of two null vectors equal to 0 if they're not connected at all. So I think there is promise still with these ideas, but maybe it is more limited than what Dr. Cruz is showing us right now.
Okay, then give me 1 minute, please. Almost connected the other equipment. Then I am going to put off my microphone here. Okay. Okay, now I can hear to you. Excuse me, I have the problems with open the file here. Okay, finally, excuse me. Um,
No problem.
okay, we have here the file, and okay.
Okay, so that looks like Mathematica.
Yes, is an interpret of Mathematica. Yes, and here we have the different cycles that we were speaking. This is the first one that we want to. Because I am trying to use the most simple complete graph. Then
So you can annotate that, I guess, right? The software allows you to annotate it.
excuse me.
You can mark that the figure that on the graph now. You can mark it, right?
Yes, and then excuse me. But I can. Okay, I must to change to PDF like, annotation. Sorry. Okay, then we have here the different kind of graph. And first, I don't put enough attention to your comments before, but the idea is that here in H and the idea is that here in H vertex, we can what's wrong here? Okay, no. Here we can have different kind of objects. Then we can have vectors or multi-vectors or something like this, and then we can establish a relation between them. Then the objects here are of the any class that we share, and then we can establish the relation. Then if we go to the different cycles in the complete graph, then we can find different complete cycles in this graph. I understand that Professor Garrett are looking for complete cycles here because they are the expression in the table of products for the Clifford algebra. Then I think that this is the idea. The weight of age relation can be defined in arbitrary form. Then it is not necessary here to speak about one special value, but we can think it in general. Then the idea here is that if we have one class of object, for example, I'm going to use this notation. For example, we can use one, no, sorry, O1 uh, have a relation with O2, and then we need to define these relations. Then in the graph theory, we have an adjacent matrix. Then we have this kind of adjacency. For example, we have one, two, 1, 3. We have here A, 2, 3. In this graph, those are 0. And here, in principle, we have I to 1, A3, 1, A3, 2. Then we have here the adjacent matrix, but we are not defining the properties of A in this matrix. Only we know that they are related. Then we can define this, and Professor Garrett I remember he take the table I don't remember RAB, no? After AB,
BA, yeah.
BA next.
Yeah, that's it.
That's it. Okay. And then this table are here. It's the same for okay, here I need to put the same. B, EB, AB, BA.
I should
And then,
write it outside.
Excuse me?
Multiplication, put it outside. A, a second on the left side. Put it on the left side.
Okay, okay.
A squared is equal to 0 on that multiplication.
Okay, okay. Yes, here we have, and here A, B, AB, BA. Okay. And here we have the multiplication table. This is 0, and the same here, and AB is in only I not remember what value, but
Yeah, that's AB. AB is an idempotent, so AB times AB is, yeah, that's right.
No, that's right.
Where it is 0, you have 0 A then.
this is 0
then A.
and A. Okay, okay, and and so here is BA, and here we have beam, and here we have 0.
Yeah,
And
exactly.
okay, we have the A 0, okay,
AB.
AB, okay,
And 0.
0, okay, and finally 0. Beam and A beam.
No, that's
And
0.
oh, that's 0. AB
Then
is
relay.
0. Okay, and BA.
Yeah, that's right.
BA. Okay, if we have this, then we can define in the cycles in terms of the adjacent matrix these relations. But here we have we can go back, and then we can take this like an adjacent matrix, but I am seeing that this is not enough because we need 4 vertex, because this is with the same. This is we need one more here, and then we have this. The idea is that the A by A is the identity. Then we left this, and AB is this relation that we have here. AB. This is beam. This is, and this is BA. And with AB have not relation, that then this is not. This is not in the graph, and A with BA is A with BA but A with BA is A. Okay. Then here, this have this value. This is AB, and this is A, and B with A is this is BA, and this is in this B with B is 0, okay, and B with AB is B. Is B, and is A. AB with the A is A.
Shouldn't that be A? Like AB on A is
AB with A.
A, right?
This is A, and then this is okay.
Okay. I have to be careful of the direction of the arrow, right?
Yes.
It's the order of the product.
Okay. And I'm going to erase that.
Okay. Maybe when you're done with this, maybe I can show you one picture that's closely related to your picture, but it also shows you the relationship to a geometric algebra for any dimension. Very simple. So when we have time, I can share a screen with this other picture I have, which is very closely related to what you have here, but it's more general. And also you can then label all the vertices with null vectors. You don't have to have, for example, here you have AB as a idempotent, whereas A itself is a null vector and B is null vector. So the picture I'll show you, you label all the points by A1, A2, and A3, and then you have a multiplication table, which is very similar to what you have here with AB and so on, but it's more general.
Yeah.
It would just take me a minute to show that. So when we can, let me share a screen and I'll show you.
Okay,
I
am going to stop the sharing. Yes.
Okay, so maybe I can just share it right now then. Let me see if I can, okay, let me do that.
Okay.
And let's see if I can get to it. Okay. Let's see if I can share it. Okay, here it is. Okay, here. I can make it big here. Okay.
Yeah, that's good.
So here's what I wanted to show you. So what we're, instead of just using A and B, I'm using AI and AJ. Okay, so AI and AJ are just null vectors. You square them, you get 0. But now you can see, so what you're doing for your table, you're replacing A and B with A1 and A2. So A2 is B in your multiplication table, and A1 is A. Okay, so you can see if you have n idempotents, A1 to AN, then this tells you how to multiply any two of them together. In this case, the inner product of AI dot AJ is 1/2. So AI dot AJ is equal to 1/2 if I is distinct from J. If AI is equal to AJ, then it's 0, as we had before. So you can see this is a multiplication table for distinct AI and AJ. Okay, and you can see the relationship to geometric algebra is simple. Well, here you have it. AI times AJ plus AJ times AI is equal to 2AI dot AJ. And for distinct, well, if I is not equal to J, you get 1/2 because the delta function is 0 when I is not equal to J. Well, 2AI dot AJ, so for distinct I and J, then you have AI dot AJ is equal to 1/2. Now, that gives you the geometric algebra G1N, and that's what I'm explaining here. So the geometric algebras GN1 and G1N are given by these. Now, if you have it AI dot AJ is equal to minus 1/2, then you have to change that multiplication table like this. Okay, you still have AI times AJ is AI AJ, but now you have, when you multiply AI times AI AJ AI, you get minus AI. So remember before in your table, A times BA was equal to A, but now because this is more general, it's for a more general geometric algebra then. So that's how it comes out then. And if you, so in other words, if you're looking at the geometric algebra G1N, that's the positive one, but it, let's see, yeah. Okay, G1N, and let's see, where's the other one? Oh, here. Okay, so yeah, so GN1 is where you take F1 squared is equal to minus 1, and then you have E1 squared all are equal to plus 1 then. So GN1 is where all the, okay, so in this case, AI dot AJ is equal to minus 1/2. The inner products are minus 1/2. And for 1N, then these are all equal to plus 1/2. So the idea is that is making any graph by using these two geometric algebras for the null vectors then. Well, anyway, so that's the idea. I can stop sharing then. But
where the graph theory enters is only in the sign, isn't it?
Well, yeah, you're naming the vertices of the graph with these null vectors. A1 squared is equal to A2 squared is equal to A3 squared equal to AN squared. And then the other algebras, that's for the algebra GN1. That's where you have, okay, so you have this geometric algebra 1N. That's where all the A's corresponding to that geometric algebra have inner product 1/2. But for this geometric algebra here, okay, so this geometric algebra generated by E1, F1 up to Fn is exactly the same as generated by A1 up to AN plus 1, because we have N plus 1 here, where all these inner products are equal to 1/2. But the other geometric algebra, if you change the signature N1, then it's just F1, E1 up to EN then. So that's something that I didn't understand before, but it's very easy to show, well, that's the progress I've made in the last couple of weeks, actually. So you see, two geometric algebras correspond to algebras of nilpotents, where the inner product of those nilpotents are 1/2 or minus 1/2. So this one here is for minus 1/2. for the nilpotents, and this one is with the plus 1/2, which is pretty interesting, actually, I think. And that's the idea that I'm trying to get at.
But
And this general relation, I can send you this the PDF file for that if you like.
sure. But the connection with graph theory that you made initially associated each vertex with a null vector, correct?
That's right.
And then each directed edge with a scalar product.
Yeah, so here I'm
Two
saying
null
that
vectors.
if A1 dot A2 is 1/2, then you can think about that as an arrow from A1 to A2. But if A1 dot A2 is equal to minus 1/2, then we're talking really about another geometric algebra that associated with it.
But this, I guess, in the graphs that Eustace showed us, all the edges are directed, right? But in your case, you're talking about a scalar product, and the scalar product is necessarily symmetric, right? You assume that the
Yeah,
scalar
the
product
scalar product, well, I was thinking about that as directing so if A1 dot A1 dot A2 is 1/2, that means you have an arrow from A1
Right.
to A2, okay, connecting
That's just
A1 to A2.
that's
But
the
if it's
way you
minus 1/2, then but then you need a different geometric algebra to represent it though. So maybe it's not completely general as Dr. Hayes
well,
is
what I was trying to get to was that um, it's perhaps easier, instead of considering directed graphs, if you considered undirected graphs, that is like where the edge has no direction, but then associate the sign of the scalar product with the weight that you assign to that edge. So
Yeah, that's certainly possible because since they're all null vectors, you can say 2A, 2A1, 3A1, or you can associate the direction just by changing the sign. A nilpotent, if you multiply it by any scalar, is still a nilpotent. So then you can connect it with it. If you say 3A, that means 3 circles around A then. In this way, maybe that's a better way of looking at it then. So that's another way of assigning weight to the nilpotent. Of course, it's still a nilpotent, so the weight that you assign to it can be, it's the degree of the edge then, if it's positive or negative, and so on. So, but an undirected graph, that's right. Maybe it's better just to, if it's undirected, then if 2 edges are connected, then you can use just AI dot AJ is equal to 1/2 for everything, for any 2 distinct vertices. And that corresponds to the geometric algebra G1N. How does that sound?
I think it makes sense, because what you mean by complete graph is more closely related to an undirected graph.
I think that's true. So that's actually what I'm trying to sort out now on this final paper for ICA CGA. I would like to talk about graph theory a little bit that we've been discussing here even. Of course, I'm wondering what the status of our papers with the Ojevich book is right now too, of course. Maybe Dr. Jesus can answer that question, what the status of those papers are. Anyway, I can stop my machine and go back to.
But in fact, at the moment, I think that the multiplication table define to us and different matrix. No?
Well, that's right. So that's right. So my notation is not standard notation. I guess your notation, you're still using the adjacent matrices as people use them and adapting your language with the standard matrix notation then. But I'm actually identifying, that's right, I'm identifying these geometric algebras 1, n or n, 1. Well, for just an undirected graph, then it works out just fine with all the inner products of the vertices are 1/2 or minus 1/2 for undirected graph, or you can make it minus 1/2, but it's more convenient really to use the 1/2. You don't have to worry about the signs then all the time. Well, it's just a different multiplication table, though, of course.
But if I recall correctly, originally you were considering all Clifford algebras.
Well, that's the thing. I was confusing ideas together, and I never really had exactly the relationship between the nilpotents, so the null vectors, and the degree of the geometric algebra. But now I clearly understand. I can send you there's 2 pages on it of how geometric algebra 1n is related to distinct null vectors having inner product 1/2. That's for 1n, or n1 corresponds to n plus 1 null vectors with inner products all equal to minus 1/2 for distinct vertices of the graph.
But
So,
suppose we had a geometric algebra 2, right? So can we still associate null vectors with the basis?
well, that's where this that's where the table comes in of all these. There's many different isomorphisms between these geometric algebras. So actually, you can use complex matrices to represent many of them with either the positive 1/2 or negative 1/2 signatures then with the null vectors. So you can almost talk about all of them because of the algebra isomorphism between these various geometric algebras expressed in these tables of isomorphic geometric algebra or Clifford algebras that is famous from Lunesto's work or many other people as well, of course. And of course, I give that in this matrix gateway to geometric algebra. I give those tables in that book as well.
So you're saying that you could, like, given Clifford algebra 1n and another Clifford algebra m1, that with those 2 Clifford algebras you know how to associate null vectors.
Well, basically, yeah, you know how to associate them with complex matrices because the relationship is very clear between complex matrices and Clifford algebras then.
But I'm still focusing on the
the
notion
two
that
signatures of those null vectors, either ai.aj is equal to 1/2 or ai.aj is equal to minus 1/2. Between those two, you can basically cover all the other geometric algebras as well by complex matrix.
But without going to matrix representation, if you just deal with representations in terms of these underlying Grassmann algebras. So
you reduce the geometric multiplication in geometric algebras to these tables 1 or table 2. So for example, so you think about expanding the real number system to include A1, A2 up to AN plus 1, and that's equivalent if all the inner products is equal to 1/2 for distinct vertices, then then you get, that's the multiplication table for the geometric algebra. I know, pretty strange table. That encompasses the multiplication table for this geometric algebra. That's 1n, okay? The geometric algebra 1n. On the other hand, if you want the inner products equal to -1/2, well, that's this multiplication table. Then that's the multiplication of the null vectors then. So either you have this one, and that's actually identical with the A's and the B's, okay? Just have A1 equal to A and A2 equal to B, and you get exactly this table, the same table that Jesus put up.
But if I have a geometric algebra G22, then how do I know which null vectors? Like we need a set of 2 null vectors, right? We need.
Okay, well, the geometric algebra G22, that's all. And if you look at the table of geometric algebras, those are real 2x2 matrices then, or, if you go on the list, then if you're looking at only real matrices, then that corresponds to signatures G and N, okay? But those geometric algebras are isomorphic to, no, you have to look at a table of them to see which ones they are. But
the only geometric algebras we know that have null vectors so far are the 1n and the m1s, right? So they have. So we need to.
Well, of course, when n is equal to 1, then you have G11. Okay, that's of course that's a double real number system where you have multiplication of or n corresponds to 2 real matrices multiplying. In that case, it's the double real numbers they call it, so for n it's double n by n matrices then. That corresponds to the multiplication of the geometric algebra. You have to look at those tables. They're interesting tables which relate these isomorphisms. There are many isomorphisms that it's hard to keep them straight, of course, but that's part of probably the reason why geometric algebras aren't universally accepted, just a small community, because, well, there's so many identities and so on. But that's the interesting thing. At least the multiplication table for these geometric algebras is very simple. Basically, those are the geometric algebras N1 corresponding to this table, or 1n corresponding to this table, which is pretty unusual. And you'd have to look at the tables to see exactly what geometric algebras we can reach. I think you can reach basically all of them, actually. And then, of course, that's the way I'm thinking that graph theory, at least for undirected graphs, as we just mentioned, corresponds to just AI dot AJ is equal to 1/2 for distinct vertices. Okay, but if you want a vertices that's not connected, then you have AI dot AJ is equal to 0. So those are vertices which are not connected to the other vertices then. So you can just throw in those null vectors to get vertices which are not connected to the other vertices then. And that's when the inner product is 0 then. So for a directed graph or undirected graph, AI dot AJ is equal to 1/2, or if it's not, if you have a vertices that's not connected to the other ones, then it's just you put in null that have 0 inner products with this other null vectors in. But all the vertices are named by null vectors. So Okay, well, anyway, that's the idea. I'll send you that. I'll send you, it's only 2 pages, as you can see. And it gives you the relationships. This is very important here, but it's only 2 pages. So I'll send you that right after we finished.
Okay. Mhm.
Okay, I'll stop sharing them.
Okay. Well, I think I've sort of exhausted my questions. I don't.
Well, it's interesting what Hayes is trying to do. He's doing it using the standard notation with adjacent matrices being the same. But this is quite different to what I'm attempting to do. Well, of course, you're mixing category theory language with your presentation, whereas I'm not so familiar with that language as I should be, actually. But I missed that when we were graduate students. That the next year after my year of graduate students had to take category theory, but I missed that. I wasn't required to study category theory as a graduate student.
Okay. Well, perhaps we can discuss our next meeting. First of all, I guess when should we have the next meeting, and sort of where would we go from here?
Well, actually, I think probably I don't really want to meet next week because I'm trying to get them to extend their deadline. I'd like to finish this paper for this other, this ICA CGA stuff, and I haven't. I run it the calculate. When I was in Mexico now, I wasn't able to do anything because I didn't have Mathematica, but I have Mathematica now, which simplifies these calculations. It's difficult to do any of these calculations by hand. It's too easy to, even with such an easy multiplication table, you're still, well, you still run into trouble calculating things.
Well, I'm wondering if we've sort of reached the end of our sort of series of discussions about sort of duality. Like this sort of series of discussions started with some notions of duality, and the presentation that Dr. Sobchak made about compatible Grassmann algebras as a representation for geometric algebras. And I understood, I think, that you considered this representation in terms of a pair of Grassmann algebras as a kind of duality, I guess, somehow related to the duality.
Well, yeah, it's still that way because now you still have AI times AJ plus AJ times AI is equal to 1. So that's a kind of a duality, but people, of course, don't think about duality. Well, now you can have it either equal to 1 or minus 1. So when it's equal to minus 1, that's another kind of duality that's people don't consider. So if AI times AJ plus AJ times AI is equal to minus 1, well, that's not considered duality. But for geometric algebra, that's you can have these AI times AJ plus the geometric product AI times AJ plus AJ times AI is equal to 1. That's a duality relationship. Well, in the sense that normally AI, they don't consider duality as, well, usually expressed in terms of the partial derivative being dual to the vectors and covectors.
Mm-hmm.
But it is tied into that idea. But this is related by the geometric algebras G1n and Gn1, where you have plus and minus 1 duality, whereas the standard idea of duality is, well, it was forms or vectors and covectors. That's quite different idea, really.
Yes, and I guess in all of this discussion about Clifford algebras, I did not see something that I could directly relate to the notion of a covector. I mean, the notion that you have two compatible Grassmann algebras, that's attractive because it's simple to think of one of these Grassmann algebras as vectors and the other Grassmann algebra as covectors in some sense. Right?
That's right. That's right. That's what leads to the matrix representation. But this now is actually giving a representation in terms of these null vectors, which have square 0, and the inner products are equal to 1/2. But that's still the geometric product that we're talking about, which is, well, I think it's surprising because I didn't understand exactly the relationship, but now I clearly understand the relationship between the geometric algebras G1n and Gn1 to these null vectors, which have square 0 and have inner product equal to 1/2 or minus 1/2. Like I say, that's AI times AJ plus AJ times AI. That's the Clifford product, or matrix product if you like, but equal to 1 or minus 1. Then that's a different kind of concept of duality, though, that we're talking about, though.
You're talking about introducing a scalar product of an element of two different Grassmann algebras, right?
Well, actually, we're talking about one. You can think about it as just being elements in a geometric algebra, but I don't specify what geometric algebra they're in. Well, I want to do that. I want to specify exactly the relationship. But it's only recently I could understand clearly the relationship between these null vectors and these geometric algebras 1n and n1. But that's closely related to these complex geometric algebras, which are isomorphic to almost all the other. Once you allow complex matrices, for example, the Pauli algebra or the Dirac algebra is a complex matrix algebra. So that's the signature 1, 3. Okay, that's called, well, Hesnes calls it space-time algebra. But 1, 3, that's the same thing as the complex 2x2, 4x4 matrix algebra. Okay, that's related to 1, 3, 1, 3. So that's where you have 4 null vectors which have inner product equal to 1/2. That's equivalent to that. So that's a very important geometric algebra. 1, 3 is complex 4x4 matrices and their matrix equivalent. Or the even subalgebra of that is a Pauli algebra that we all know. So there's just many relationship between these various geometric algebras that we're talking about.
Well, in any case, I'm not sure that there is a sort of logical way to proceed from this point in sort of in this line of research.
Well, I think the graph theory is the way to go with it myself. That was why I brought it up now, because Dr. Cruz's picture, of course, is exactly what my AI times AJ, just let A equal to A1 and B equal to A2. And that's exactly the table that Jesus was showing us. Exactly the same.
But the graph theory that Jesus is talking about involves a kind of generalization to higher order graphs. Like, so what you would call an ordinary graph would be order 1, like G1. It consists of a set of edges, but then there's a concept of a two edge, right? So that this is a relationship between graphs. and in between, and that's a graph of graphs and graphs of graphs of graphs. So this generalization to higher order, I I don't see how that connects
Well,
to.
no, we do. We just talked about that. You identify a vertices with a null vector, say A1. But if you want it connected to itself, then you put either minus the what degree of connection minus 3a or plus 3a for positive. You know, so an undirected graph, you label all the vertices with null vectors, which have inner product 1/2. So that's undirected. But if you want it directed, then you associate weights with those null vectors, and then you get the weights then as well. You know, the weight, so if it's undirected graph, just A1 up to AN plus 1. And that's the geometric algebra G1 comma N, that corresponds to it. Or it's matrix equivalent. We know what the matrix representation of any geometric algebra is. So we have a matrix representation then of the graph then as well.
In fact, some people used to use a undirected graph equivalent to a complete graph. Because it's in the relation, if we relate one vertex with another and give one weight to this relation, and then if we invert the relation, we have a minus weight, then this is equivalent to a complete graph in general, are used as in this way. Then I think that the idea of using not a direct graph is equivalent to complete graph, and then we can find in those those kind of graph the relation that are in the in the way that you put in the product table. Then and each vertex can be one AI and AJ, like you put it in the one n Clifford algebra or n1 Clifford algebra.
Then that's right. So your A1, A2, A and B would just represent two vertices as you're thinking about it. So
Yes.
Yeah, the simplex really, the two simplex idea. So instead of if you use just A and B, you don't represent 3 points, but you represent 2 points, A1, A and B, and then A dot B is equal to 1/2, and then A squared and B squared are null vectors. So your picture works fine for just two A and B are the two vertices then. That's the simplest case. But if you have 3 vertices, then we're talking about undirected graphs where A1 squared equal to A2 squared equal to A3 squared is equal to 0. And undirected means that their inner product is equal to 1/2. That's an undirected graph. Now you can also say it's a complete graph if you wanted to, I suppose, but maybe for a complete graph, then you can associate the weight. So let's see, if you have, that's right, if you have, well, yeah, so it's either 2 would be where you just put weights on the points and they indicate the order of the point and the order of the vertices, and that should work too. By the way, this CGA conference, there was a guy that gave a lecture using Grossman algebra for vertices, just pure Grossman algebra. He doesn't put a metric on it, but he had very complicated figures and did a lot with just Grossman algebras and graph theory. I don't remember the details of his talk, but I should probably dig that up and try to understand better what his talk was about, just using Grossman algebras for graph theory in some way or another. Maybe that's exactly what he's doing, naming vertices with null vectors and then just the weights of those vertices represent the order of the vertex or the degree. I guess they call it degree. I guess the vertex is how many times the vertex is connected with itself. Is the weight of the graph, and the vertex, I guess.
Because my idea is that we can start with the table of products, and then we can build a graph. Then with this graph, we can find different kind of properties that show to us the different relations. And in the original idea is that we can use complete graph because they are in some they are giving to us the different the different kinds of products that we are defining. Then if we change the table, then we change the properties of the product. Then we can represent in this kind of graph the different products that we are using. And after that we have that graph, my idea is that we can convert in a tree graph, because if we convert in this way, we can find one hierarchical relation in these algebras, and then after we can go to establish some required properties for convert these algebras, for convert this graph to a category. Then we can speak about the category of this graph, but it's needed to have some properties. This is the way that I think that we can understand more the relation between these algebras.
Okay, yeah, I would like to, not this next week, but in 2 weeks, I would be happy to give one last presentation on what I see now. I think I can show you how exactly to relate the Clifford algebras to graphs in a consistent way, which I really wasn't able to do before. And then we can maybe even just half the hour, and then Jesus could continue. Well, I'll send you this 2 pages that I have, and it explains clearly the relationship between, these Clifford algebras G1n and n1 to the two signed. So a complete graph is basically an undirected graph, and then we can assign the weights to get the weighted graphs, and then connect that to the category theory ideas, I hope. So that would be my idea then. So in 2 weeks, I wouldn't mind. I hope to finish this paper by that time, and I could present that paper.
Well, I wonder if it might be advisable to wait just 1 week longer, so that our next meeting could perhaps be on, I guess that would be February 15. If we took 3 weeks,
February.
perhaps February, yes, February 15. Perhaps that would
Okay, that's fine.
Jesus also a bit more time.
Yeah, that's right. I get into trouble with these calculations, actually. I'm trying to streamline them with Mathematica now, but I've had a lot of trouble. And of course, just keeping the ideas of graph theory straight is a task as well. So,
Eustace, did you want to make a sort of an extension of what you discussed today, say in 3 weeks from now?
Yes. I am going to continue with this work. Then we can show to you my progress.
Okay, so maybe that's a good plan then. Is if we met in 3 weeks' time, that being February 15, and then we could sort of split the time between Dr. Cruz and Dr. Sobchak.
Yeah, I will send these 2 pages that I was showing you immediately after our talk now, and you can see exactly the relationship better maybe when you have it in front of you.
Okay. Do you have any more questions or suggestions, or shall we say that we're done for today and we'll see each other in 3 weeks from now?
Yes, I think that is okay for me. Mm-hmm.
Okay, great.
Okay, I look forward to it. I think I can, in 3 weeks for sure, I'll be finished with it. I've got to be finished with it. I've just spent 6 weeks in Mexico thinking about this stuff. And now, well, at least I have Mathematica at my disposal now, which is very helpful. So.
Yeah.
I have to admit that most of my thinking these days has been devoted to quantum mechanics and working with another friend of mine on this subject that I discussed briefly before about Bohm's version of quantum mechanics and sort of what has happened sort of in that line of research.
Well, that's where I think these complex 4x4 matrices can now be represented in terms of these null vectors, four null vectors, A1, A2, A3, and A4. That must have a relationship to quantum mechanics, I would think, because, the speed of light, that's very basic. And the fact that you can represent the complex matrices by 4 null vectors, which have inner product 1/2, is pretty amazing to me. At first, in fact, I thought you had to go to higher dimension, but it's very clear relationship between this geometry. As I'll send you these sheets today, just a couple of sheets, and you can understand how it works.
Okay, well.
But then maybe you can give a talk then following on the quantum mechanics aspect of it, we'll keep,
Yes, it's so far in my mind it seems quite distant. I mean, it's not closely connected at all, except for, as you say, in terms of relativistic quantum mechanics. But maybe there are connections there that I'm just not
well,
seeing.
quantum mechanics uses the Dirac algebra, right? You use the Dirac algebra all the time, don't you?
Or perhaps Pauli algebra, right? If you're
Well,
interested
okay,
in
that's even subalgebra, the Dirac algebra.
but a lot of quantum mechanics is discussed without even mentioning spin, and so that means that you don't need even the Pauli algebra at all. You're interested in algebraic relationships that aren't really of a matrix nature, right? They're of a more general, perhaps operator nature, but
Okay, well, we can explore it maybe.
yeah. So, okay, I'll keep that in mind for the meeting after our next. But we'd have to be prepared to sort of change our subject area a little bit and focus
Well,
on.
sure, I'd be very happy to talk about Bohm representation of quantum mechanics. I've certainly read about it.
Maybe I would make, if to me that would feel like getting a little bit back towards physics and less mathematics, perhaps.
Okay,
Or at least pure mathematics.
good.
All right, so let's meet again on February 15th, the same time.
Okay.
Okay. Okay.
Right. Well, goodbye for today then.
Well,
Okay.
take care.
Bye. Thank you.